Hello, everyone. In this video, we'll talk about the singular value decomposition. We'll set it up, and then we'll conclude the discussion about it in the next video. It's a very important application of the last few results we discussed, orthogonal diagonalization of symmetric matrices. So let me start with reminding you of what we did in the recent videos. First of all, last time we proved that if a matrix is symmetric, then it's diagonalizable with orthogonal matrices of eigenvectors. And conversely, any matrix that possesses an orthonormal basis of eigenvector is symmetric. And more in general, we saw that a square matrix is diagonalizable if and only if there exists a basis of eigenvectors. So the main question that we want to work on today is what happens if the matrix that we start with is not even symmetric to begin with. Here's the prototypical example. We can get a matrix A, which is m by n. And this size of the matrix means that I can multiply vectors v inside Rn by the matrix and get vectors in Rn. So when I try to even write down the equation for an eigenvalue and an eigenvector, this doesn't even make sense because A times V is in Rm and lambda times V is in Rn. So this is impossible. We can't use eigenvectors and eigenvalues to make these matrices look nice. Of course, we can't diagonalize them because they're not square, but we would like to do something similar with a matrix that is not symmetric. So then the next best thing that we can work with are what are called singular values. So the setup is the following. As we said, the matrix A, which is size m by n, takes vectors in Rn and spits out vectors in Rm. When I transpose it, the size of this will be n by m. So you can think of this matrix A transpose as taking vectors in Rm and spitting out vectors in Rn. So this is sort of the game that we're going to play, and we'll use it to define the following, to give the following definition. We'll say that a certain number sigma, it will turn out that these are always bigger than or equal than 0. We say that it's a singular value of the matrix A if there's a pair of vectors v in Rn and u in Rm such that the following holds. So these equations look a lot like eigenvalue equations. So A times V has to be equal to sigma times U. And we also require that A transpose of U is equal to sigma times V. In this particular setting, we say that U and V are respectively the right and left singular vectors corresponding to the singular value sigma. So we are trying to replace the idea of an eigenvalue and an eigenvector with that of a singular value and a singular vector. And that's what this definition does. It gives us singular values and singular vectors along with them. Okay, so now the question is, well, the same methods as before don't work. These matrices don't even have a determinant because they're not symmetric. So how do we find singular values and singular vectors? Let's start with the singular values. We'll do the following. Again, remember that A goes from Rn to Rm, A transpose goes the other way. If I do A and then A transpose, I'm taking a vector from Rn and spitting back up another vector of Rn. In other words, for V in Rn, A transpose AV also belongs to Rn. So the size of the matrix A transpose A is n by n, and it's a square matrix. Since it's square, we can look at its eigenvalues because we know what an eigenvalue is for a square matrix. And I'll find the eigenvalues of this, and I'll write them down in order from the biggest to the smallest. here's a little fact that we're not going to prove, but it's crucial for this construction. Not only is A transpose A a square matrix, in fact, it is symmetric. And since it is symmetric, by the spectral theorem, it is diagonalizable. And so we know that we can take these eigenvalues. There's n eigenvalues to it. Moreover, another fact that you can prove is that all of the eigenvalues of A transpose A are bigger than or equal than 0. So when I write them ordered like this, I will always mean that the first few eigenvalues, the first k, are strictly bigger than 0. And the last from k plus 1 to n, those are all going to be 0. So now I'll define the singular values for all of the non-zero eigenvalue of A transpose A as their square roots. In other words, after this process here of looking at the eigenvalues of A transpose A, we get a list of singular values that are ordered and they're all positive numbers. Let's have a look at an example. Here's a non-symmetric matrix A. So the first thing you want to do to find the singular values is to look at A transpose times A. When you compute that, well, by just looking at the sizes of this, you'll realize that this is a 3 by 3. So let's just compute it out. The first entry is going to be 0 plus 1 plus 4, it's 5. Then we have 0 plus 0 minus 2. This is a 3 by 3. No, it's a 2 by 2. Oh boy. Wait, give me a sec. I wrote it wrong in my notes. Of course, we're computing the transpose, and that will be a 3 by 3. But the transpose of A is this matrix: 0, 1, 2, 1, 0, minus 1 times A, which is 0, 1, 2, 1, 0, minus 1. Okay, now when we compute this, we get 0 up here, 0 here, and we have minus 1 here, 0, the second row, 0 in the third row, and well, in the middle entry, and then we have 2 here. Then I'll do it again, minus 1, 2, and then we have 4 plus 1, that's 5. Okay. Yeah, I think that's correct. But now give me a second and I'll double check these eigenvalues. Okay, sorry for that interruption. There was actually a typo in the notes that I wrote down. I wanted this number to be a 1, not a negative 1. So now everything should work out fine. If we compute the product between these two matrices, we get a 1 in the first entry, 0 in the second, then we get a 1 up here, 1 times 0, 0 times 0, that's a 0. Then we get a 1 in the middle entry here. We get a 2 here, and we get 1 down here, a 2 in here, and a 5 here. Now, if you compute the characteristic polynomial of this, you'll see that you get the following polynomial: minus lambda times lambda minus 1 times lambda minus 6. So the eigenvalues, and I'll write them in order from the biggest to the smallest, are 6, 1, and 0. The singular values attached to it are going to be the square roots of the positive eigenvalues. So there's going to be two singular values, sigma 1 and sigma 2, and they're going to be the square root of 6 and the square root of 1, which is nothing but 1 itself. Okay, so that's how you find singular values. Compute A transpose A and find the eigenvalues of it. Now, the next question is, how do we find the singular vectors? Well, a singular vectors mean we have to find two sets of vectors, the vectors vi and the vectors ui. So finding the vi is relatively straightforward. We have the eigenvalues of the matrix A transpose A, and this matrix is an n by n matrix. So its eigenvectors will be vectors of Rn, which is what we need the VIs to be. It's a symmetric matrix, so we can pick an orthonormal basis of eigenvectors for it, and those are going to be our VIs. So the VIs are the orthonormal eigenvectors of A transpose A. To define the UIs, we'll have to go through a little bit more work. For all the indices smaller than the last singular value, so whenever there is a singular value, we define them like this: 1 over sigma I times A times VI. The reason why we define it like this is that what we actually want to happen is that, well, multiply this by sigma I, and you get that AVI is equal to sigma I UI. So we are forcing sigma I UI to be a singular vector. So this is the equation for singular vectors. It's their definition. So we define them like that. And by just definition here, it's not too bad to verify that these vectors UI from 1 to k are actually orthonormal to one another. So let's check it. If I compute ui dot uj, that's the same as saying u over sigma I avi dotted with u over sigma j avj. But then, well, I can rewrite this like this: sigma I sigma j here, and then I have avi dot avj. But well, let's see. AVI dot AVJ. Now let's do one more step. I can move A across the dot product and transpose it. So here I get sigma I sigma j, VI dotted with A transpose A VJ. Now VJ, by definition, is an eigenvector of A transpose A. So this becomes lambda j over sigma I sigma j vi dot vj. Because what we used here was that A transpose A vj is equal to lambda j vj by the definition of the vj's. Okay, so now what happens next? We have these expressions here. If I is equal to j, then ui dot ui, by following along this, this chain of equalities up here, becomes lambda I over sigma I squared vi dot vi. But, well, sigma I is the square root of lambda I. So lambda I over sigma I squared, this is equal to 1. And vi dot vi is equal to 1 because the vi's are orthonormal. So we use two things here. The first is that sigma I is the square root of lambda I. And the second is that the vi is a unit vector. If ui is different from uj, so if I is different from j, then we get instead lambda j, sigma I, sigma j, but now we're computing vi dot vj, and vi dot vj is equal to 0 because the vi's are an orthonormal basis. So here we're using that vi and vj are orthogonal. Okay, well, but these two bullet points together, 1 and 2, show exactly that the UIs are an orthonormal basis for whatever they span. There's only k of them. So the next step to find the other UIs is to complete this UI through UK to an orthonormal basis of the whole space Rn. So it doesn't really matter much which choices you make here, as long as you make the whole basis orthonormal. The way you do that, well, we'll comment it in an example, but I mean, one thing that you can always do is to extend U1 through UK to a basis. You can always do that because U1 through UK is a linearly independent set, basis of Rm. And then once you've done that, you can use Gram-Schmidt on the new vectors. So that the new basis is orthogonal. And then you normalize. So this can always be done. I'll say a few words after the example we're going to make about this, but not much. Okay, let's pick up the example from before. This matrix here is a 1 here. The singular values we computed, they're square root of 6 and 1. If you work a little bit with this symmetric matrix A transpose A, you can find a basis of orthonormal eigenvectors for it, which are these V1s, V2, and V3. Just compute a basis for the eigenspaces, make them orthogonal within eigenspaces, and then normalize everything. Then we can finally compute the U1 and U2, which are the other singular values. In this case, they're given as follows. So U1 is 1 over sigma 1, which is square root of 6, times a V1, or maybe I'll write everything out. So A is 0, 1, 2, 1, 0, 1. And I multiply this by 1 over root 30 V1, which is 1, 2, and 5. Maybe let me take a little bit more space. Well, when you multiply all of this out, you get 1 over square root of 180, 6 by 30, times the following vector. It's 0 times 1, 2 plus 10, get the 12 here, and here you get, what is that, 1, 0, 5, so that's a 6. Okay, so if you simplify this out, you get that, yeah, 180 is 6 times the square root of 5. That seems right. Yeah, because this is, it's 36 by 5. And so you get 1 over root of 5 to 1. Okay, let's compute V2. It's a similar thing. This time, well, we have to divide by the singular value. The singular value is 1, but I'll divide immediately by the coefficients that is in front of V2 as well. So I get square root of 5 times A, 0, 1, 2, 1, 0, 1, multiplied by the vector V2, which is 2 minus 1, 0. And when I compute this out, I just get exactly what's written here. Get a minus 1 in the first entry and a 2 in the second entry. Okay, so this U1 and U2, automatically, without us having to normalize anything, they're already normalized. They are an orthonormal basis of Rm, which in our case is R2. In this particular case, as I hinted at before, we didn't have to complete, we don't have to complete this basis U1, U2 to a basis of Rm, simply because like we already have enough vectors here. But if m was bigger than 2, then what we would have done is what I hinted at before. You complete the basis U1, U2 with other vectors, and this can just be random linearly independent vectors for now, but then you can apply the Gram-Schmidt orthogonalization and you normalize them. These two processes will not touch U1 and U2. because those are already normal, they're already unit vectors, and they're already orthogonal to one another. So when you do Grange meta-normalization, this first part of your basis will not change, and the rest will be made orthonormal instead. So the outcome will be exactly an orthonormal basis for Rn. Okay, let me just briefly, no, let's do it next time. No, let's go on. We'll do this, and then in the next video, we'll wrap everything up and state what the singular value decomposition is. You know what? I'll leave this to the next video as well. So we'll break it up more nicely. Okay.